Just a second. I think it's all set. So please feel free to test the screen sharing.
Yeah. Seems to work. Seems to work fine, right?
Yes.
Okay.
It looks like you have a great office.
I hope you come visit soon.
I never reject your invitation. We'll wait for maybe 1 or 2 minutes, and you have 90 minutes, and you can go over time if you want. But, anyway. I'm sure more people will join in along the way, so maybe we should start. Welcome everyone to Harvard CMSA Quantum Maths and Physics Seminar Series. It's our great honor today to welcome Professor Clay Cordova, a Nobel Family Professor of the University of Chicago. Clay Cordova, who is known as a young leader of the young generation of physicists working on quantum field theory and various new emergent exciting topics. His talk today will be his new work just appeared today on arXiv on non-invertible duality defects, especially in 3+1 dimensions. Let's directly welcome Clay. And also I want to remind the audience, please feel free to interrupt. Raise your hands or interact with Clay. And so let's welcome Clay. Please take over. Thank you.
I already made a blunder and didn't unmute myself. Okay, can everybody hear me and see my screen? Yes?
Yes.
And please just shout out questions. I can't see the raised hand, so just interrupt me. Okay, so I'm going to tell you about non-invertible duality defects. It's the subject of a recent paper that I wrote with Choi, Sin, Lam, and Shao. That's on the archive now. And I would also like to highlight an overlapping paper by Omori, Katie, and Zhang with very interesting results as well. So I encourage you to look at both. And there is also a recent lattice paper which spurred many of the ideas in this area, which I've also listed here. So let's get started. So in this audience, I probably don't have to remind you that the modern approach to symmetry in quantum field theory is topological operators. This is the perspective, for instance, advocated by the generalized global symmetry work. And here, let's just remind ourselves that if we have a symmetry, which is a Q-form global symmetry, there will be some topological operator, U sub G, which we can place on manifolds M D minus 1 minus Q inside our spacetime. So here, this is some manifold. This D is my spacetime dimension. And this whole gadget is some topological operator. Of course, the index Q here is supposed to remind us what's charged. So Q equals 0, that's ordinary symmetry. We have charged local operators. Q equals 1 will be the hero of today, and that's the one form symmetry case, and we'll have charged lines. Now, whenever you have topological operators, you should inspect their fusion algebra. And for general symmetries, general higher form global symmetries, this will be group-like or invertible. What does that mean? Well, we'll have sort of the obvious fusion, which is that UG1 of M, UG2 of M will be equal to UG1, G2 of M. So the picture, of course, is that we have a topological operator on M. Here's G1. We have another parallel operator a little bit displaced from it, G2. We bring them together and we get a unique third operator, G1, G2. And this is, if you like, the sort of general paradigm of higher form symmetries. We allow topological operators of various dimensions with this restricted kind of fusion law. And there are slight generalizations, for instance, to higher groups, but those won't be that important to us today. Now, we could turn this equality here around. So here we have symmetry in quantum field theory, and we said this led us to topological operators, but not every topological operator is quite so simple as I've made it out here. So the fusion of topological operators can be more general. It can be non-invertible. What do I mean by that? I mean that I could have Ui and fuse it with some uj. And in general, I will get a sum over some abstract index k. So here ij and k are just labeling some the topological operators in my theory. And so I'd like you to note two things here. So first, in this sum, we could envision, of course, that there's more than one term. So here, when we collide two symmetry-like two invertible defects, we get a third invertible when we get a unique thing on the right-hand side. More generally, we can get a sum. And another thing that can happen is that we can have defects of various dimensions here. So we'll see both of those generalizations today. Now, of course, many examples of this kind of phenomenon. Juven, you raised your hand?
Oh, well, I can just ask Erica. So maybe just clarify for the audience, when you say this sum of these operators, how should I think about these physically? So this may be some kind of a splitting. Does it implies maybe some simple way we can understand other than the formal notation of this sum?
It means that correlation functions in the presence of this product are the same as the sum of correlation functions with each term inserted here. Mm-hmm. But perhaps when I give some examples, it will seem more transparent.
Okay, yeah. Yeah, I think maybe, yeah, I'm just trying to motivate. Maybe there are some audience understand this even better in some ways. Well,
a fusion rule in general, like the kind I've written here, is a rule for replacing a nearby product of operators in a correlation function with a sum of other operators in a correlation function.
Mm-hmm. Yes. Yeah, I'm trying to think about more. Sorry for no, I'm not trying to make trouble to your talk. I'm just,
that's fine.
You're understanding this. I think whether people will agree with me, like for experimental this, does it mean this splitting of some channels that we have a different ways to fuse the operators and go to different outcome? Does it imply just other than the formal notation, which I also use, but I was just motivate maybe some people speak up. Is there some kind of splitting of the Hilbert space in different sectors, something like that?
I think.
Yeah, but I just want to initiate some discussion, make people.
I think that starting from this abstract discussion, it is not obvious what the dynamical consequences of such a more general fusion rule are, but it's also not obvious until you worked out the details what the consequence of this fusion rule is. So what I would say is that we should get started with this more general fusion rule, and then we'll derive some dynamical consequences later in this talk, in the same way that we derived some dynamical consequences of having symmetry in our past lives.
No problem. One more thing, just because you also mentioned this higher group, and you said these are not essential for your talk. Just for clarification, in the case of higher group, which for example might mix between zero-form symmetry or zero symmetry and one symmetry, in that case, either of them can all have a categorical or this non-invertible fusion rule. Is that right? If you want to generalize that rule,
the fusion in the higher group setting, the fusion algebra of each defect individually is invertible. So everything involved is invertible.
Yes, but I say if you want
a general category, but anyway, I don't want to explain that.
Okay, no problem. Thanks. That's fine.
Excuse me, I have a question.
Yes.
Here you mentioned about the correlation. So when you define topological operator, do you have to specify some kind of Lagrangians which you can define correlation so that the correlation of a topological operator do not depend on their position and the shape?
Yes. So I'm working. My picture here of the setup is that I'm in sort of an abstract field theory, where the defining data of that field theory are some list of operators and correlation functions. And I'm zooming in on a special class of operators, these U's, which have the feature that they are topological. That is, they can be placed on some manifolds of some dimension, but their correlation functions do not depend on small perturbations of those manifolds.
Thank you. There's a related question. I think those topological operator is kind of like a symmetry transformation operator. So whether you can define them by themselves before you define the Lagrangian or Hamiltonian, so that they themselves satisfy certain algebra. So they are they are symmetries.
Well, yeah, I'm quite sympathetic to that point of view. I mean, you could say that this is a symmetry class here, this simple one, and we'd like to then investigate theories that enjoy that symmetry class. And indeed, I think that this generalization to the non-invertible situation, as you well know, should be viewed on the same footing. That you should think of this as some kind of algebra and some kind of generalized symmetry algebra. And we'd like to explore theories that have this symmetry.
Okay, but in this algebra point of view, what makes them topological? In a sense, do they commute or something like that?
Well, the statement that they're topological is a statement that when we generalize to include all other operators in whatever theory we happen to be in, the correlation functions of these quantities do not depend on small deformations of their supports.
Okay, thanks.
Okay.
Question here. I assume that when you bring U1, Ui, and Uj next to each other, then first of all, they should be parallel. And
Yes.
second, there shouldn't be anything in between.
Yes.
Okay,
Yes.
thank you.
Yes. Thank you for that clarification, Nadi. Yeah, I'm envisioning a situation just like here, where they're parallel. They're on sort of the exact same manifold. I'm just going to collide them point by point with nothing in between. Okay, so of course, many important examples of this is known. Let me just briefly mention.
But then I have a follow-up question.
Yes.
What does it mean different? So imagine Ui and Uj are both two-dimensional. Then in the sum on the right-hand side, you said you have defects of various dimensions.
Yes.
How can there be another defect of another dimension? Because it should have support on the same manifold that Ui
Yes.
and Uj were supported.
Exactly, but and that will indeed occur. So imagine, for instance, that Ui wraps some manifold M. So the Ui is on some M, and Uj is on some M, and we collide them. Then the sum over defects here may involve homology classes inside M. So they could be lower dimensional. It doesn't have to fill all of M.
Oh, I see. Thank you.
Yeah. Okay. So let me say some prominent examples that are well known and appreciated.
Can I ask one more question?
Yes, Juven.
About the fusion rule. So is that here, the way we write this more like a group law or even the general fusion rule, the fusion algebra for this fusing, for example, Ui and Uj, they commute. Is that right? Ui fused with Uj is the same as Uj times Ui? Is that always true?
It need not be if they're codimension 1.
Oh.
If they're higher codimension, then you can move them around each other, and this question doesn't arise. But if they are, yeah, in general, they need not be.
Okay, but okay. Will you concern this issue in this talk or not really?
We will not encounter that, though.
Okay.
The defects that I'm studying are codimension 1.
Okay, thank you.
Okay, so prominent examples, Verlinde lines.
So let me understand that better. Do you have examples of these non-invertible symmetries which are non-trip? Sorry, let me rephrase this statement. Do you have examples of codimension 1 such that it goes beyond ordinary symmetry, or is it only when it's higher codimension?
I will today give an example of codimension 1 that is non-invertible.
So this is an operator that acts on the entire space.
Yes.
Okay, looking forward to it.
Okay, so so prominent examples are Verlinde lines in rational theories, rational CFTs. So for instance, we'll later encounter today the Ising fusion category. So in that example, there's a line which is the identity. There's a line called eta. This is a Z2 zero form symmetry line. And then there is something else called sigma, which is sometimes called the Kramers-Wannier line or the Kramers-Wannier duality line. And their fusion is that eta times sigma equals sigma times eta equals sigma. And sigma times sigma is 1 plus eta. So it's this sum here, which means that this sigma is non-invertible. And we would like to generalize this to higher dimensions today.
So I'm sorry that I still come back to that. So this is codimension 1, as in my question.
Yes.
It is still a billion. My question was if there is I misspoke when I asked the question.
Okay, what was your question?
Is there an example like this which is non-abelian?
You mean where if I had multiple and I flipped the order, I'd get something different?
Yeah.
I do not have an example like that.
With symmetries, you can have that.
With symmetries, I can have that. I don't see any reason why I cannot have it for the non-invertible case, though we do not yet have an example.
I see.
There is an example already in 1 plus 1 dimensions.
In
that case, yes. So in Ising squared, in this Ising squared case,
In Ising squared.
yes, there is a duality defect, and it's not self-dual. So it's not a Tambari Amigami type, but it's more general. That duality defect explains why the Ising squared CFT is self-dual under non-abelian gauging. In that case, the dihedral group P8.
I see. Thank you, Ifan. Yeah. Okay. Okay, so that's an example that people already know about. And another example that people already know about are closely related anions in 2 plus 1D. You could view these as something like a non-invertible generalization of one form symmetry. Okay, and so there are perhaps other examples, but let me move on and say what I'll do in this talk. So in this talk, what is our main goal here? I'd like to construct non-invertible defects. In fact, I'll give a construction that will work in many dimensions, but I'll focus on 3 plus 1. And then, so these will generalize the Kramers-Wannier. And we're going to explore 2 general properties. One is the fusion algebra. And the second is their dynamical consequences, some simple ones. Of course, I don't know all of them. And we'll give some simple example. Okay, any questions about this preliminary part? Okay, then let me move on to defect construction. So our main input will be a duality. So we'll envision that we have some theory tau. This will be a theory with some GQ symmetry. Here I'll be in general space-time dimensions, but soon I'll specialize. And we'll imagine that this theory has an interesting property, namely that if I gauge this GQ symmetry, so this is GQ gauged, that it comes back to itself. So let's imagine we have a duality like that. Now, let me also specialize. So this discussion, of course, could work for many choices of GQ, but for me, GQ will always be finite. And in the cases that we're really interested in, it will be abelian, because we'll be in a 3+1 dimensional setting, and eventually GQ will be a one-form symmetry, so we'll be forced to be abelian. And so I can run this construction for general GQ with those properties, but I'll specialize in this talk to GQ equals ZNQ just for simplicity.
I have a question. Is the demand that it's abelian somehow necessary, or is it just to simplify the discussion?
In the case of a zero form symmetry, it is not necessary. And Ifan already gave us a nice example of something that can happen in that case when you use non-abelian zero form symmetry. But I will be primarily interested in the higher form symmetry case, and higher form symmetries, that is Q strictly greater than 0, are always abelian. So that's why I'm going to specialize to that situation.
But for zero form symmetry, when it's non-abelian, can there be such an isomorphism?
Yeah, just give an example of Ising squared. There's a D asymmetry. The theory itself do under D8 gauging. But that's the only example I know.
But the
So it's not
dual
very
symmetry,
common.
but the dual symmetry is different from the one we gauge.
That's right. Exactly. The dual symmetry is rep D8, and that's why the duality defect is not self-dual and it's non-abelian.
Okay.
So the fusion of the duality defect with its dual depend on the order that you fuse them. That's I think that was what Nati was discussing before.
Okay, let's maybe discuss that example in more detail afterwards. So, okay, I'd like to notice something important here, which is that if we gauge GQ, we get a dual or new G symmetry, which is of a different form degree in general. So this, of course, is generalizing the orbifold symmetry in the case Q equals 0 and D equals 2. So if you look at this, you would say that duality of the kind that I'm talking about here would only be possible. So let's call this duality star. It's only possible if Q equals D minus 2 over 2, which of course is an integer. So we can have Q equals 0, D equals 2. We can have Q equals 1, D equals 4. We can have Q equals 2, D equals 6, etc. And I'll mostly focus on this example. Okay. So let's get on with the story of constructing this defect. So we're going to look at a Dirichlet interface. So what will I do? So I'll separate my space-time into two regions. I will call these regions L and R. In the left part of space-time, I will put the theory. And in the right part, I will put the theory where I have gauged, I'm specializing here to Zn just for simplicity, where I have gauged Zn Q. And let's call the separating locus M. That will end up being the defect world volume. So what will be the action of this theory, of this setup that I have here? So the action will contain three pieces: an integral over the left part of space-time of the Lagrangian for my initial theory, whatever it was, an integral over the right part of space-time for the Lagrangian of my theory, now coupled to some Q+1 form gauge field. So this AQ+1 is a dynamical Q+1 form Zn gauge field. And in general, I could also have some SPT. Now, different choices of this SPT, this action for this Q+1 form gauge field, will end up defining different kinds of defects. And for simplicity, I will just set it to 0 in my talk. But this is just for simplicity. So we're going to focus on this situation. Now, I have to tell you what's going on. Yes.
Could you clarify how do you specify the Dirichlet interface?
I'm about to do that.
Okay.
Yeah.
Is it by some way of condensation or some?
Just wait. So I have to tell you what's going on at this interface, and in particular, that means I have to tell you what's going on with this gauge field A. So what will we do? So along the interface, which locus was called M, we place Dirichlet boundary conditions. That means A Q+1 restricted to M is 0. Okay. And I should remind you that we're assuming a duality here. So I'm assuming that this theory is isomorphic to the original theory that I started with. So this is a comment. If I did not make that assumption, I could still define such an interface, and it would be an interface between two different theories. Here, we're going to get a defect within the theory itself because this gauge theory is isomorphic to the initial theory. Okay, so some properties. So this interface is topological. Why? Well, if you change the shape of the interface by putting a little bump, this adds the field strength for this gauge field, but this is a flat gauge field because it's a discrete gauge field. So we have a topological interface. A second property that is generally true is that, remember, I reminded you above about this dual symmetry, that when we gauge, we get a dual symmetry. So let's write down what this dual symmetry is. So in R, in the region R, the dual symmetry comes from operators of the form integral over a closed cycle of AQ plus 1. So this is the dual symmetry. And so here, this is an integral over S, and we could think that this is some operator eta of S. And I would like you to note that since AQ plus 1 evaluated on the wall equals 0, this defect, let me call the defect D, we would have D times eta equals eta times D equals D. Because when I bring these to the wall, they just annihilate. So here, this D, I'm going to call it a duality defect. I've constructed it using this Dirichlet boundary condition. And because of the duality assumption that I put in at the start, this is a defect in one quantum field theory, and it is codimension 1. Any questions about this? So this is the construction.
I have a question.
Yes.
Do you have some particular global symmetry only on the duality interface?
I'm not really discussing what lives on the duality interface.
So it could be there are actual global symmetries on the interface.
Yes, it's possible. I'm not really sure of any universal answer to that at the moment.
Okay, thank you.
More questions?
Actually, a quick question. So do you mind briefly explaining a little bit more about why the interface is topological? Like moving the domain wall is the same as adding DA?
Well, I'm not sure what to say. I mean, this is the field strength condition.
Uh-huh. Okay.
No, one simple thing is that the domain wall may have a tension. So changing shape of the domain wall may increase energy. So that seems non-topological. So there's
Yes, but I'm coupling my theory to a flat gauge field. Is the point. So if you imagine you represented the Zn Lagrangian as a BdA kind of term, with B the Lagrange multiplier field, then what I'm telling you is that the way I'm coupling my theory T to B and A only involves A, not B. So the equation of motion for B remains intact. If by contrast I had allowed my theory to couple to both B and A, then the domain wall would be non-topological.
Okay.
So that's the condition, is that if you think about it in that kind of more continuum Lagrangian language, it's the fact that the way I'm coupling my theory only involves A, but not B.
Okay.
Okay, so let's continue then. Okay, so first general property we wish to discuss is the fusion. So what is the D times D fusion algebra? So let's draw a picture. Let's consider space-time, which looks like M times R. And here will be So this is M here, and this is the R direction. And here will be a defect. And I'll put another one nearby to it. And there's nothing in between, and they're parallel. And I have this slab region in between them. And in this slab region, I have gauged Z and Q with Dirichlet boundary conditions. So here and here. So we're going to use this setup to evaluate the fusion algebra. Essentially, we'll see that the fusion algebra comes from just studying this gauge theory in this slab with these boundary conditions. So let's do as a warm-up case 1 + 1 dimensions. So there's a simple kind of trick to understand what the fusion must look like, which is, let's look at D cross D. Let's suppose that this contains, it may contain in general many terms, but let's suppose it contains the identity line. So this is the identity line. So maybe I should also comment, in 1 + 1D, this manifold M would just be S1. So this cylinder picture is literally what's going on. So let's suppose D times D contains the identity line with some unknown coefficient, Y. We'll return to this coefficient presently. Now I claim that if you know this, you immediately conclude that D times D should equal to Y times the sum of I equals 0 to n minus 1 of eta to the I. And the reason is that I already explained to you above that D times eta equals D. And so if I've put this in, then if I replace here D with D eta, then I find that eta must appear in the fusion with the same coefficient. And now you can note, what is this sum really? This is just the expected sum over Wilson lines in the slab gauge theory. So remember, I said that we can get the fusion by studying gauge theory in this slab. Well, that gauge theory is a sum over Wilson lines in this slab, and this is that sum.
May I ask a question that I think I should have asked earlier?
Yes.
So you see at the point where after gauging, it's the same theory.
Yes.
The coupling constants are not the same because they're mapped. So it's not another the same. What's called positive epsilon could be minus epsilon on the other side. So let's deform now the theory. It should still remain topological, but do you deform them such that they would be the same or not?
Sorry, are you talking about the Eisen case? Is that why you said epsilon?
I can talk about any theory because
okay,
in many cases the duality acts on the coupling constant.
Yes, and what that shows you is that for that example with the epsilon operator in the Ising model, is that if you pass epsilon through D, you don't get epsilon again, you get minus epsilon.
Good. So if you deform the theory, when you deform the theory by m times epsilon,
that breaks
the thing, but you can still do that because your duality is still, your setup is still valid.
Yes.
And you will have to deform by plus m on one side and minus m on the other side.
Yes.
But then your analysis of diffusion will not be so simple.
Yes, that's possibly true. I would like to be in a situation where D is actually where the theory is actually invariant under D.
Yeah, but that's one point. So I can ask the same question another way. Let's perturb Ising with this coefficient m. So we bring from the exponent factors of epsilon. Some of them are on the left, some are on the right, and some of them are on the slab.
Yeah.
And
I would say that then D defines an interface between two different theories. One is the theory, the Ising with plus epsilon times some coefficient, and the other is the Ising with minus epsilon times some positive coefficient. Those are two different.
And if once you have the defects in the region between the defects, you flip the sign, what do you do? Then it is the same theory.
Well, what will happen in that situation is that, so in this region you'll have theory with plus epsilon. This region you'll have the theory with minus epsilon, and this region you'll have the theory back with plus epsilon.
Good.
So this
Okay,
composite thing should be still in that situation a defect in the initial theory, and it indeed will be.
Good. But now when I try to move the defects in order to fuse them, I have additional insertions in between, which complicate the discussion. And also, it's not just gauging or ungauging. It will not be merely a gauge theory in the slab region. It will be a gauge theory with some deformation. Maybe you want to say that you don't discuss that. You're only at epsilon at m equals 0, where you don't insert anything, and then I can't ask my question.
Well, certainly I can retreat to that situation, but I have the feeling that this does not, that even as an algebra of, although I'm not 100% sure, I have the feeling that as an algebra of interfaces, this formula will still be correct.
Yeah, I think you're right about that, and it should better be correct. The question is only how to define the left and the right hand side.
Yeah. Okay, let's come back to your question. For now, let me retreat to this this more conservative.
Okay.
Okay, so good. So this is the expected sum over these Wilson lines, and what remains then is to fix this coefficient y in this fusion. So where does the coefficient y come from? Well, this is just the normalization in this Zn0 gauge theory, normalization of the partition function. Okay, and probably everybody who's ever played with gauge theory explicitly knows what this should be. So then we should have y is 1 over, it's always h0 for this gauge theory, order of h0 in S1 times interval. But now some slightly interesting mathematical thing to comment on is that we here have a relative cohomology. And that's because of the Dirichlet boundary conditions. And okay, this is just one. So that cohomology group always has the unique trivial element, and that's it. And so we get 1. And so over here, this y is 1. And what I've derived for you is the so-called Tambara-Yamagami fusion rule. This algebra of topological lines. We saw that for the case n equals 2, this happens in Ising. More general ends happen in different situations. Right, I want to stress this is an algebra. It can occur in various different theories. But for, just as an explicit example, I think, if I'm not mistaken, SU2 level n mod U1 realizes the Zn version of this. Okay. Now let me mention a key property here. key property that makes this interface, this duality defect, different from an ordinary symmetry is the way it behaves with respect to local operators. So here's the region L. Here's this duality defect D. Here's some local operator, which is charged under Z and 0. And the duality defect is topological, so I could try to move it past this. I could try to sweep it past this. And if I do that, okay, there's nothing in the left region now. But now this operator becomes non-local. So this is local here. And this is now non-local. And it has a eta line attached. This is this eta line. So that's sort of tautological from the construction, but I'd like you to notice that that is quite different from an ordinary symmetry. An ordinary zero form symmetry should map local operators to local operators. Here we see we're outside of that framework. Okay. So this was our 1 + 1D warm-up. Let's now come to the main show, which is 3 + 1 dimensions.
Question?
Yeah.
Previously, did you develop that D times D is equal to that sum, or just it contains that sum?
Previously, did I well, essentially what I derived is that it's equal to this sum, right? D times D is the gauge theory in this slab. And that gauge theory is just a sum over Wilson lines, right? That's the explicit, this is the explicit partition function of that zero form Zn gauge theory in this slab.
I mean, can the right-hand side contain something else?
Can the left-hand side,
Sorry, right-hand side, right-hand side.
the right-hand side contain something else? No, I think not. I think that D times D is this gauge theory partition function.
Oh, okay. Mm-hmm. But if the matter in the gauge theory has some non-trivial dynamics, it could have something else, right?
Well, I think sort of tautologically, this is just the gauge theory partition function because I'm sort of gauging and ungaging. I think it's important that this is a universal fusion rule that is independent of the dynamics of T. Once you know that T, that's sort of the point, is that once you know that T is invariant under this Zn gauging, you get this fusion rule.
Mm-hmm. Okay, thanks.
Okay, so let's go back to 3 + 1D. We now just sort of repeat the same story. So now we're doing a one form symmetry, Zn1. So again, we're going to have D times D, compute it by gauging in the slab M times interval. So we'll have a sum over gauge fields. What are gauge fields in the slab? So the equivalence classes of those. That we're going to have to sum over, those will be some objects in relative cohomology. Again, the relative cohomology is because of the Dirichlet boundary condition. And here I'll use essentially Poincare duality to say that this H upper 2, those gauge fields, is the same as H lower 2 of M Zn. So then the gauge theory partition function in the slab can be represented in a simple way. D times D will be equal to some unknown coefficient y, which we'll fix in a moment. times a sum over gauge fields. And I just said the gauge fields here are labeled by this. So this will be S in H2 of M Zn of eta of S. These are the one-form symmetry defects. So coming back to the question that Nadi asked at the beginning about how does it look when you have an example, how does it look when the defects are of different dimensionality? Here you see an example. So this D here is codimension 1. It wraps a 3-manifold M. When I collide two of them, I get a sum over defects of lower dimensions, like this. Okay, so then let's fix the constant y. Y comes from the normalization of the partition function again. Now for a two-form Zn gauge theory. So we have some stuff in the denominator to figure out and some stuff in the numerator to figure out. So same relative cohomology reason, Dirichlet boundary conditions. And this is 1 over n. So we've derived the fusion. Let's summarize.
Excuse me. Yeah, I have a question on this.
Yes.
So as operator relation, when the D times D, it became something with a lower dimension. But how do you determine this lower, where the location of this lower dimensional S? They're supposed to be equivalent, and but as operator relation, it looks strange because
well, that's one way to understand why there should be a sum here. So here I'm summing over every 2 cycle in M.
I see.
And that's how I dodge your question. I don't say that it's located at some particular 2 cycle. That sounds very strange. I say that it's kind of a condensation of the one-form symmetry defects. I should say that this is what, kind of physically, that's what this is. This thing here, you could think that this is like a condensation.
I see. But you don't. Let me see. Because the way you write it could be means a sum over one representative with a 2-cycle class, but that's not what you do.
Well, because the etas are topological,
yeah,
which explicit representative you pick does not matter.
Okay, yeah, thank you.
Okay, so let me summarize the fusion. So this duality defect can absorb one-form symmetry defects. Since this was Zn, we have eta to the n is 1, but we could have done it for a more general finite abelian group. And then we have sort of the money equation, which is this one. So that's the fusion algebra that we're discussing. And just like in 1 + 1D, I would like to highlight a key property.
I'm confused about something.
Yeah.
What does this 1 over n mean? So does it mean that if you compute something with 2 defects on the left-hand side, the answer will be linear combinations with coefficient 1 over n,
Yes.
partition function with insertions of eta?
Yes.
And how do you normalize all these things? Is there an issue of normalization of the
well, so just to say, I mean, I defined eta. Is the, if I think of it as the dual symmetry, it's exponential of I integral of A2 in this case over some surface. And eta is invertible, so its normalization is somewhat sacred.
No, I have no problem with eta because eta to the n is 1, so I know how to get the normalization, perhaps
Yeah.
after the overall phase. But what about the normalization of d? So for the first equation, d times eta and eta times d equal d, doesn't matter how you normalize d. But that somehow is important in the more interesting equation.
Yes.
How did you normalize d?
Well, we define D as gauging in half of the space-time, and that explicit construction gives an unambiguous normalization of D.
You see, for the Wilson line, as your eta, there's always an ambiguity in how you define the Wilson line by adding a local counterterm along the line, which in this case you have set because eta to the n is 1.
Mm-hmm.
And maybe you can also set it because it's topological. I'm looking for a more invariant way of defining the normalization of D.
But I think gauging is an unambiguous way to define this defect.
Right, but if you have an actual quantum field theory, there might be a local counterterm on the defect, which at the very least has the effect of changing the normalization.
But on 3 manifold, I don't see an immediate local counterterm we can write down on the Ward volume of D.
Well, the integral of 1 would be 1. It would not be topological, but that's typically what you have to worry about.
Sure, but I don't see a topological local counterterm.
Mm-hmm. Okay.
Yeah. Okay.
Sorry, just make sure the statement. Are you what the Suhan was saying, or maybe not? He's asking is that the adding counterterm here is like adding SPT to the wall volume, the D into
Well,
the D, or no?
I think the worry is not about the phase, but about the normalization. And I don't think that there's a way to change the normalization by adding any while preserving the topological nature of the definition.
But let me have just one comment. So here we give an explicit construction of D, and the normalization is unambiguous. Once we have constructed such a D, we can always stack D with another 2 + 1D TQFT on top of it.
Yes, of course.
For example, we can stack with a BF theory in 2 + 1D, and that would change the normalization or degeneracy in some way.
Yes.
Yeah.
I mean, there's all. I mean, once you have one defect, you can stack and get many defects. Yeah. Okay, but Nadia is right that normalization will play an interesting role later. So keep an eye on it. Okay, so let's go to this key property that I wanted to highlight. It's very analogous to the 1 + 1D situation, which is that if I have D, and here's L, and here's R, and here is some Zn1 charged loop, that if I bring the loop across D, it acquires a topological surface. And the surface goes on to the wall. So here's an eta surface. Okay, so this is all I wanted to say about the algebra defined generally speaking. And next I'd like to list some examples and then tell you a little bit about what we know about the consequences of this algebra. Okay, so let's start with a nice example where everything is quite explicit. An explicit example will be U1 Maxwell theory. So just to clarify what I mean U1 Yang-Mills theory with no matter at all. So this theory is defined by an electromagnetic coupling tau, which is complexified. So it has the usual Yang-Mills coupling, the usual electric charge here, E, I'll call it G, and it has a theta angle part. And what are the symmetries of this model that will be important for us? Where, well, there's a U1 electric one-form symmetry, and there is a U1 magnetic one-form symmetry. This is the symmetry. And the objects charged under this are Wilson lines. And here the objects charged are 't Hooft lines. Now, what are we going to do? We are going to gauge Zn1, which I will think of as a subgroup of the U1 electric symmetry. So let's track what happens after I do that. Okay, so what happens if you gauge that? So the dynamical gauge field A, that's the gauge field defining the U1 Maxwell theory, is dynamical, will get replaced if I gauge this Zn subgroup of the electric symmetry by A over N. And the entire action is quadratic in A. So this tells me what happens to tau. Tau is then replaced by tau over n squared. So the Lagrangian looks the same after this gauging, but tau gets changed. The form of the Lagrangian looks the same. Okay, so in general, this will be an interface between two different theories. So in one region, we'd have the theory with coupling tau, and the other region, we'd have the theory with coupling tau over n squared, separated by this interface from gauging this electric Zn1 form symmetry. But sometimes it can happen that tau and tau over n squared are equal as quantum field theories. And that can happen due to electric magnetic duality. So electric magnetic duality says that the theory labeled by tau here is the same as the theory labeled by A tau plus B over C tau plus D for A, B, C, D integers and AD minus BC equals 1. So we could perhaps this theory is equal, this theory with new coupling tau over n squared is equal to the original theory if I use one of these transformations. And indeed that can happen for specific values of tau. So for instance, if I use the S element, that's tau being identified with minus 1 over tau. I would like minus 1 over tau to be tau over n squared if I'm trying to make these two theories the same. And this happens when tau equals IN. So going back to this, undoing this complexified notation, that's vanishing theta angle. And G squared equals 4 pi over n, for n some integer. So at this special tau, we have a duality defect.
Is the partition function invariant under this transformation?
Well, sorry, is it invariant? There can be.
Is there any anomaly here?
There can be gravitational counterterms. There are gravitational counterterms. And this is a good moment to say, I didn't ever clarify to what extent, just going over back up to this discussion here, the very beginning, sorry, where is it? Here, when I said the main input was a duality, T equals T mod G, you could ask, in what sense do I mean this equation? And I mean it sort of exactly as theories coupled to GQ, so including the counterterms for GQ, but modulo other counterterms that do not involve this GQ. So in that context of SL2Z, there is a shift in the Euler and signature counterterms, the curvature couplings, but that's okay. The construction can still works on the nose with those.
I see. Thank you very much.
Okay, so we can also say more. So we could write this defect a little more explicitly. Using a Lagrangian. It's a free theory, so we better be able to do it. So let me write the action. So I'm going to specialize to this tau is in. So then I get n over 4 pi integral over the left half of space, which I'll call x less than 0, of dA left wedge star dA left. Then I have a similar thing in the right half of space, which I'll call x greater than 0. And there's a gauge field there, dA right wedge star dA right. And then I have something on the wall. And what do I have on the wall? That's a 3-dimensional locus. I have a mixed Chern-Simons term, A left wedge D A right. Okay, so this wall x equals 0 supports this mixed Chern-Simons term. With the properly quantized coefficient. Because n was some integer in my construction. And I should say at this moment, this is very similar. This kind of the fact that there are mixed Chern-Simons terms that come up in S duality transformations is something that goes back to Gaiotto and Witten. And one way to understand it is just to think about the equation of motion. So if you demand that there are no boundary terms here in the equation of motion, you'll get that dA left at the wall is minus I star dA right. So this is from vanishing boundary terms. And then here I use the electromagnetic duality at tau is in. I can rewrite this as saying it's 1 over n times d a right dual, where this is the dual gauge field. And this 1 over n is exactly what you would have expected from the Zn gauging. So that's one way to understand how to think about that mixed Chern-Simons term. Perhaps even more satisfyingly, although I won't talk about it, one can carry out this entire construction in a lattice model of U1 gauge theory. And then you can also derive this very explicitly. So that's one simple free example. Let me mention briefly, I won't really discuss them, just enumerate some further examples. And then we will go on to some more interesting dynamical consequences. So some of these are on the continuum, some of them are on the lattice. So SO8 Yang-Mills has Z2 times Z2 one-form symmetry, and it has a Z2 times Z2 duality defect. And this example can be generalized in a variety of ways. You could add matter, preserving the one-form symmetry. So some class of matter preserves the one-form symmetry. You can also generalize to theories whose Lie algebra of their gauge group is more generally SO4n. Okay, so that's one kind of example.
Sorry, Clay.
Yes.
So since these are codimension 1 defects, so they also naturally act on local operators. But so far, you have only discussed how they act on line operators.
Yeah, thank you for the question. So the question is, how do they act on local operators? And I can't tell you any universal rule. I think it is theory dependent. But what I can tell you is that their action is a kind of order 2 operation, in the sense that the fusion rule, where did it go? Here. So these etas don't act on local operators.
Yes.
So, for instance, in the S duality setup, I think D acts on the local operators as S duality acts on the local operators.
That's right. But the question is there, well, I guess you will say there's a phase ambiguity again.
There's a what ambiguity? Sorry?
A phase ambiguity?
No, I think, well, I don't think so. In how D acts on local operators. No, but I don't know any universal rule for it, is my point. I just don't know. I don't, as far as I know.
Mm-hmm.
Intuitively, this is non-rigorous, but intuitively, I think that D is, on looking at the local operators in 3+1 dimensions, D will look something like a Z2 symmetry, but I'm not 100% sure.
Mm-hmm. But in the Maxwell case, it will just map the field strength to the dual.
That's correct. So, but I mean, I could take linear combinations and get some things that are even and some things that are odd.
Mm-hmm. Mm-hmm.
Okay, so
yeah, I think what I was asking was, is there like I also fix the coefficients? So would you say that in this case the coefficients like 1 over square root of n, when you shrink this codimension 1 defect circling this local operator, just like in 1+1 dimension, because of non-trivial quantum dimension? Yeah.
Yeah, I mean, because there's a quantum dimension.
And if you can play a similar game in the CFT by considering this operator in the time versus on the spatial direction.
Yeah, that's right. There's a non-trivial kind of quantum dimension of 1 over root n. So yeah, that sounds right, though I haven't chased it all the way through.
Okay. Thank you.
Okay, let's say another example. SUN n equals 4 Yang-Mills at tau equals I has, because of n equals 4 S duality, the equivalence with SUN modulo Zn gauge theory. Let's write it as this way. PSUN, which you can think of as the initial theory where you have gauged Zn one-form symmetry in the notation that I was using before. So this theory will have a duality defect. And let me also mention, it is not my work, but this beautiful result by Omori, Katie, and Zhang. I encourage you to read their paper, which is that PSUN at theta equals pi has a duality defect. And I really mean this PSUN at theta equals pi. And I should also maybe as an aside mention this is not exactly the same duality defect construction that we have. It has a slightly different fusion rule because they construct it in a slightly, they sort of gauge in a slightly different way than we did. This is a close cousin. Okay, so those are some continuum examples. There are others in their paper. There are also some lattice examples. I mentioned lattice U1. There's also lattice ZN gauge theory. That's another one. So those are some examples that we know. Undoubtedly, there are many others. We're just sort of getting our feet wet here. Okay, so in the remainder of the time, I would like to go on to tell you some simple dynamical consequences of this. So let's start with a simple question. Let's say our theory, and we're going to be in 3+1D. Again, Zn, one form symmetry. There are analogs of these results and questions for different one form symmetry group, different space-time dimensions, but let's be in this very concrete case. Okay, say our theory tau has a duality defect. D from gauging Zn. Let's ask, can T flow to a trivially gapped theory? And we will see that the answer is sometimes yes, sometimes no. So in this way, we're going to derive something like an anomaly constraint. Okay. The basic point is that RG flow commutes with discrete gauging. So if I have in the UV this setup where I have T and I have T mod Zn1, which is again T, and here's the duality defect D, and this is the UV, I can run the RG flow. Now, if T could flow to a trivially gapped phase, we're going to assume that's the case and derive some contradictions sometimes, then this theory would have to be an SPT. And this theory would have to be an SPT where I've gauged this Zn1 form symmetry. And of course, it should come back to the same SPT. So this will be the IR picture. And what we're going to see is that this IR picture sometimes exists and sometimes does not exist. So questions about that? Okay. So as
what does SPT mod Zn1 form symmetry mean?
What I mean is that this is an SPT that can for the Zn1 form symmetry. And then I'm going to gauge.
Right, but does that mean that on the right, you have to sum over Zn gauge fields or not?
Yes.
How is this consistent with the duality? The theory on the two sides are the same.
Yes.
So you say that in one way of thinking about it, you end up with SPT without Zn.
Yes.
On the other side, you have SPT and you still have to sum over Zn.
Yes, as I learned actually from some of your papers, sometimes when you take an SPT and you sum over the gauge fields in that SPT, it remains an SPT. Sometimes it stays invertible. That will be an important constraint.
Okay, I don't remember this paper.
Luckily, some of the co-authors on my paper were co-authors on that paper. Okay, so let's do it in detail, Nadia, and I think it will become clear how this discussion goes. So let's say n is odd.
I'm sorry. So imagine SPT means that there's a single state in the Hilbert space. So we have some Riemann.
Yes.
We are in 4-dimensional.
Yes.
The Zn gauge theory might not have a single state.
Yes, but for specific SPTs, it will. That's part of the constraint. Let me write it down. Yeah. So we'll start. We're going to do. There's different analysis for n even and n odd. So let's write the most general SPT for a one-form symmetry background for n odd. So this is our background. And since it's an SPT, it just has a very simple classical partition function, e to the 2 pi I p over n, integral over space-time of this A2 cup A2. And here P labels the SPT, and P is identified modulo n. So that's what's going on in the left. Now let's write what the right side of this is. So this is you could think of this as being associated to the left region. Now the right side what are we supposed to do? First of all, we're supposed to take this ZSPT, this same formula here. But now I'm going to gauge. I'm going to sum over dynamical gauge fields, A2. And I introduce a new dual symmetry. Like this. So this is a new theory that, so here little a2 is dynamical, big A2 is background again. And the question is, can this be equal? So this is the right. Can it be equal to the left? Can this be equal to ZSPT of A2? So if my theory that I started with the duality defect can flow to a trivially gapped phase, there must be some SPT for Zn one-form symmetry for which this is true.
I'm still puzzled by this, the same question. The theory on, well, you flipped left and right, so it would not be easy.
Sorry, yes, the theory, yeah, sorry, over here, this, yeah,
so,
okay.
Okay, let's talk about the bottom equation. The theory on the right in the bottom equation does not have Wilson lines of A2.
Little A2,
Wilson,
yes.
Wilson surfaces of A2.
Yes.
That's not in the cast of characters.
Yes.
The theory on the left does have it.
Yes.
So how can they be the same?
Well, that's an interesting question. So you could try, this theory is quadratic here. So you could try to understand, is there some P such that sometimes the equation of motion just sets little a2 to 0 so that it kills all of those Wilson lines, Wilson surfaces. And indeed that happens. So this theory remains the left, this equation here, this is invertible if and only if the GCD of P and N equals 1. So that's a necessary condition for this kind of equation to hold. Otherwise, it's manifestly false. As you say, the right-hand side is invertible, the left-hand side would not be invertible, so it's not possible. But if GCD of P and N is 1, then then this stuff here is still invertible. And so it's possible that this invertible theory could be equal to this invertible theory. That then becomes a question about P.
But for any n, you can choose p equal to 1 always.
Yes, for any n, you could choose P equal to 1, and that theory will stay invertible.
Yes.
So Nadi, does this answer your question?
I think so, yeah. Tentatively, yes.
Yeah. Okay, so obviously, yeah, so that's a big constraint, is that we need GCD Pn to be 1. Now, we can actually, so this equation here will give rise to, if GCD Pn is 1, will give rise to some new SPT that's a function of this A. And we want to compare, how does it look compared to this one that was labeled by P? And so what this is effectively is some map on P. So the summation here this procedure of doing this sum results in changing P. P over here, it's converted over here to -1/4 times P in Zn. And here I'm using the fact that 1/4 is in Zn. So n is odd, 1/4, 4 has an inverse in Zn. So that's what I mean here. I mean the inverse of 4 in Zn. So this procedure results in a map which changes P to -1/4P. And so you can have self-duality if and only if P obeys an equation, which is that 4P squared equals -1 mod n. So if that equation can be solved mod n, you pick a P which obeys this equation, and then the SPT with that P will have the property that it is self-dual under gauging.
Okay, it should be P mapped to -1/4P with P in the denominator.
Oh yeah, thank you. Thank you. Bad typo here. Okay, -1/4P. So, and also 1/P is in Cn. Okay, so that's how we get this equation. Thank you, Pushin. And so you can think, what does this equation say? It says, first of all, it says that -1 is a quadratic residue in mod n. So quadratic residue is just a fancy way of saying that you can find a square root in Zn. But you cannot always do that. So I'm not sure if this result is like due to Gauss, maybe, that -1 is a quadratic residue in mod n if and only if each prime factor of n is 1 mod 4. So if this condition is satisfied, then namely each prime factor of n is 1 mod 4, then we can find a square root of -1 and we plug it in over here and off we go. And that is an SPT for Zn1 form symmetry, which is invariant under gauging. Conversely, if this condition is not satisfied, then there does not exist any P that could solve this equation. And so therefore, there does not exist any SPT that is invariant under gauging. So that logic leads us to this little theorem. Any theory, so the theory invariant under gauging Zn1 with an odd can flow to a trivially gapped phase only if each prime factor of n is 1 mod 4. So this is kind of like an anomaly constraint. If you have a duality defect for Zn with n odd, if n is not of a very particular type, you just can't flow to a trivially gapped phase.
What is it an anomaly of?
You could think it intuitively, although I don't understand how to make this precise yet, you could think of it as an anomaly of this symmetry algebra. But that's just an analogy, Nadi. I don't understand like anything like an SPT or anything in a one higher dimension or something like that that would make that sort of really sharp.
Question?
Yep.
At the very beginning, we said gauging, you could add one more SPT during the gauging process.
Yes.
If you do it here, I guess this theorem will be modified.
Yes. Yes, indeed. One can work out an analogous theorem, but we have not done it.
Okay, thanks.
Okay, so that's the situation for n odd. There are similar results for n even, similar conditions for n even. Maybe I'll just invite you to look them up. They're in the introduction of the paper, but the logic is quite the same. You first write down the most general SPT for n even. In this case, for n even, there's a little bit of a difference between a bosonic and a fermionic theory. For n odd, there was no difference, but for n even, there will be. And so the statement of the resulting constraint is a little bit different depending on whether the theory is bosonic or fermionic. Okay, I have one more thing to talk about, but I've reached the end of my time. I don't know, Juven, should I keep going or not?
Yeah, you should. You should keep going to say what you prepare. Don't worry.
Okay,
Just
I have one more brief thing, but first let me invite any questions about this before I move on.
Is there any simple reason that n even and n odd are different, in particular for even n both bosonic and fermionic systems are different?
Well, it's just that here, when I was analyzing the problem, I began with, let me first enumerate for you all possible SPTs, so all possible things that could go here. And that for n odd, enumerating such SPTs does not depend on whether the theory is spin or not. But for n even, it actually does. The classification of the SPTs depends on whether n is even or odd. Or sorry, whether the theory is spin or not for n even. So that's why you need to do a separate analysis there.
Okay, thanks.
Okay, I'd like to tell you one more dynamical constraint, which are constraints from modular invariance. So usually we think of modular invariance as being powerful in 2 dimensions, but here we'll get a little bit of results from modular invariance in 3+1 dimensions. So we're again going to look at the fusion rule. So the fusion rule was that d times d equals 1 over n. And we had this sum over s in H2 of m, coefficients in Zn, of eta of s. And what we're going to do now is we're going to study expectation values. So expectation values of this equation. In vacuum. So if D is on M here, this is D on M. We think, for instance, M is space. Well, let me not say that. Space will be taken to be M. And there will be some set of ground states. Which I will indicate as I, M. So I labels these ground states. And I put M explicitly to remind you that space is taken to be M. Now, in general, when computing expectation values of this kind of equation, you might think that it depends on lots of dynamics. I will make a very strong simplifying assumption and learn something from this assumption. So let us assume that eta acting on any ground state just takes it back to itself. So this is the statement that the one form symmetry acts trivially on the ground states. So we would say that the one form symmetry is not spontaneously broken. So this is an assumption in the argument that follows. We'll keep it sacred in the argument that follows, and we'll see what we can learn from this. Now, if you have in the back of your mind a gauge theory, often the one form symmetry is the center symmetry of that gauge theory, and so this is like an assumption that the vacua are confining. So you can keep that in the back of your mind as a motivating reason for taking this assumption. So, but we'll just take it here as an assumption, and we'll try to learn what we can, if that's true. Okay, so then we can, if that's the case, we can compute the expectation value of this equation in any of these vacuum states, and we'll find a very simple formula. We'll find just taking a quick square root, that this will be the square root of 1 over n times the order of H2 of m Zn. So here the defect is on m, and at an instant in time, and we get this expectation value. And here I've just used the fact that all these etas act trivially by assumption on each state. So I just have to count up how many elements there are to sum over. Okay, so that's a formula that you get for the defect expectation value, acting as an operator, wrapping all of space at a given time. In this simplified situation where the one form symmetries act trivially on the ground states. Okay, now we're going to apply this. So let's now think about modular invariance. So in that context, we'll take space-time equals y times S1 times S1. So this will be some general two manifold. And here we have some torus. And let's put the defect world volume here. So that could be M in my discussion above. And now the partition function with this space-time and a defect inserted here has two interpretations. So the first interpretation comes when I think of time as being perpendicular to D. That's what I was thinking about just above. And in this case, I would say that D acts on the Hilbert space of my theory, quantized on the spatial manifold Y times S1. And the partition function is giving me a trace over that Hilbert space with D acting on it. Okay, so that's one interpretation. The other interpretation comes when we think of time as being parallel to D. So we would take this S1 direction to be time, as opposed to the first case where I took this S1 direction to be time. In this case, we're having a trace over the Hilbert space with the defect inserted along, with the defect going along time. So this is the defect Hilbert space. Okay, so modular invariance is the statement that the partition function is equal. The partition function does not care which of these two interpretations we adopt. They must result in equivalent answers. Okay, so let's try to see what happens. Let's say that this theory with this duality defect is gapped, but not in general trivially. So it has some number of ground states on general manifolds. And let's take d y times S1 to be equal to the number of ground states on y times S1. So by that, I mean the dimension of the ground state Hilbert space. Okay, now, given this assumption that T is gapped, and moreover, given this assumption that the one-form symmetry is not spontaneously broken, I can evaluate the partition function, and I can check whether it is modular invariant. What will I find? The partition function on this setup here, this space-time with this defect world volume, will be equal to this ground state degeneracy times this formula that I found before. So 1 over n h2 of y times S1 with coefficients in Zn, the order of this group, square root. Okay, that's the sort of straightforward interpretation where I do this. But then this has to equal the dimension of this defect Hilbert space. And the dimension of a Hilbert space is a natural number. So we get a constraint from modular invariance. We get it. The constraint is that this quantity here must be a non-negative integer. And this sometimes happens and sometimes does not happen. When it does happen, we learn nothing. We learn that the modularity is consistent with all the additional assumptions we made, namely that the theory is gapped and that the theory is that the one form symmetry is not spontaneously broken. By contrast, when it is inconsistent, we learn something about the dynamics of the theory. So let's state what the general thing is, the general result is. So I'm going fast here because everybody is exhausted. So if Y is orientable, then it's always true that this is a natural number. So modularity is satisfied. If Y is non-orientable, which requires my theory to have T invariance, time reversal symmetry, this is not always true. So in that situation where we have time reversal symmetry, so I can choose Y to be non-orientable, I get a little theorem. Let me say what this theorem is, and then we'll stop. The theorem is, let's say we have a theory tau with T symmetry. And in order to avoid various complications, I'll say that the n here was 2. And it's invariant under gauging Z2, 1. So then I will say that if the one form symmetry is not spontaneously broken, then this theory is gapless. So that's the result that we prove by enforcing this modularity constraint, that there is an incompatibility for theories which are self-dual under gauging with time reversal symmetry and the assumption that the one form symmetry is not spontaneously broken. So that's the kind of result that we get in this situation. So it's kind of like these symmetry enforced gaplessness results that have appeared in the literature under similar assumptions. Okay, so yeah, go ahead.
Okay, so just make sure. So how do you prove it cannot be a symmetric gapped low energy with some TQFT?
Because for if going up to this, so I derived that this equation must be generally true, that this expression must be a natural number. And what I'm telling you is that it is not always a natural number if I'm allowed to go on non-orientable manifolds. So the choice of TQFT will enable me to produce some new integer here, which is like the number of ground states. But this is irrational in some situations. So no matter how many ground states you have, you can't. It's still inconsistent. So you'll get something like a square root of 2 or something like that, and you won't be able to escape this this kind of conclusion.
Okay. Months with T symmetry, not other discrete symmetry like charge conjugation or other type. Only
Yeah,
T symmetry.
you need T symmetry in the argument as far as we understand currently, because if you have an orientable manifold, so that is if the theory is not T symmetric, then this Y will have to be orientable. And then you can just check that no matter what orientable manifold it is, this is always an integer. This thing is you can always take the square root safely. But in the situation with time reversal symmetry, sometimes in particular for say n is 2, you can get a square root of 2 here. And then you can't fix it by changing what the TQFT is.
No problem. And this is a theorem for a 3+1D theory.
This is a 3+1D theory, and I should say also bosonic. I assumed at some moment earlier, I assumed bosonic, but I didn't spell it out for you very clearly. Yeah, okay, so this is everything I wanted to say. There's more in the paper, and there's also the complementary paper by Omori, Katie, and Zhang. So please look at that. And there's obviously sort of lots to explore. We've just dipped our toe in the water here, and I hope to tell you more about that in the future. So thank you very much.
Thank you very much. Thank you, Clay, for a wonderful seminar and lecture. And any question from the audience? I think Ivan was trying to speak up earlier.
Right. So I must have missed something. When you take the square root, is there a sign ambiguity?
Well, this is always supposed to be positive because of this.
So like in the previous page, like how did you determine the matrix element between this D operator and this?
You mean when I don't have the additional S1 to enforce that it's
yeah.
I think it's reflection positive still.
But then I have a question, because I think in the beginning you mentioned that you can, I mean, in principle, you have a family of these duality defects, which are generated by stacking SPT on top of it, right? Okay. And if you do that, what happens to this modular invariance argument? On one side, you necessarily will get a phase, but on the other side, you still want to interpret as the dimension of the Hilbert space.
So you're talking about an SPT on for what? For the one form symmetry? For what SPT are you talking about?
You can stack any invertible phase on top of your codimension. I mean, just the three-dimensional invertible phase on top of this. I
don't see any candidates for this stacking.
I think they all trivialize on this topology, right?
They're all trivialized, but you say we never have a S1 get trivialized.
For example, the Euler term will always trivialize.
Yeah, Euler and signature terms will always go away when you have a S1 factor.
Right, but you're saying this, there's a stronger statement saying that all such a possibility would always trivialize in order to avoid such a funny kind of.
It's an explicitly three-dimensional setup. So I mean, I think the list of possible, well, I mean, it's a four-dimensional setup, but the defect world volume is three-dimensional. So it's a pretty limited.
That's right.
It's a pretty limited cast of SPTs that you could add.
But if you consider going to higher dimension, this will persist, or do you think this is kind of a subtlety that?
I think it's a subtlety that you need to take it into account. I mean, we did try to take it into account in the case of 3+1, in particular, noting that the S1 factor destroys the Euler. And I mean, an important point is that since there's an S1 factor, this time, even if you were in general dimension, this world volume, Y times S1. Null bordant in general space.
That's right. That's what I.
I suspect that might be enough to.
Well, if you include spin structures, it can get more complicated.
It can get more complicated. Indeed, over here I said bosonic. I meant
right.
Yeah, it can get more complicated. I think if you have spin structures, you'll probably say something about which of them are bounding and stuff like that. But yeah, so I think in the bosonic situation, in general dimensions, you might just be safe because of the S1 factor.
Right. Right, I understand that. Related question is, so in the context of the 1+1D, so when we study this topological defects, we find that when the defect is self-dual, just like the duality defect here, meaning that this orientation reversal is same as itself, the defect can still have some kind of subtle topological anomaly, which we call isotopy anomaly. And in a 1+1 dimensional context, this is some invariant you can associate with the fusion category, this known as the Frobenius Shor indicator. I suppose in this case, there's something analogous, but
I don't feel I have a good handle on all such things, though. You know,
there's a potential sign invariant associated with each duality, whatever this higher fusion category that we have defined. There's a sign that's an invariant because the defect is self-dual.
Yeah, we haven't looked at the crossing. Yeah, we haven't looked at the crossing relation.
Right.
Yeah, it's a great question. We haven't looked at the crossing. It might appear in the crossing relation.
It almost certainly will appear in the crossing.
That's right. It should appear when you look at the crossing involving the the duality defect itself, just like how it appears Right.
But I don't have a good feeling of whether it's just a sign, for instance, in higher dimensions.
If it's self-dual, then I don't see things.
Well,
Okay. What more can it be?
maybe I'm just confused. Let me just say that, let me just go back to what I said first, which is that I don't have a good grip on this yet.
That's fine. Yeah. Thank you.
May I ask a quick question? Maybe I missed something. This is probably pretty simple. So it seems like, is there an assumption that there's no off-diagonal matrix element in D? Off-diagonal in the I label? Maybe it's just one page up.
It's not really an assumption. So here I learn, if I make this assumption that the one form symmetry is not spontaneously broken, then I learned that D squared is a multiple of the identity. So I can diagonalize D, and if needed, I'll just change the basis I to be that basis.
Oh, I see.
So the point is that I can find some basis for which this is true.
Ah, got it. Thanks.
I actually have another question about the one form symmetry. So do you know a gapless phase where the one form symmetry, discrete one form symmetry is not spontaneously broken?
That's a nice question. A gapless phase.
I don't know any, and I thought in CFTs it has to be spontaneously broken just because there's no dimensional parameter to cook up an area law for you for any Wilson loop. So naively, I would say the theorem just tells you it's always spontaneously broken.
Maybe it does tell you.
That's it.
Well, yeah.
So it doesn't really enforce gaplessness. Gaplessness is one possibility to saturate this, but it doesn't. I would say strictly speaking, it's not enforcing gaplessness. At least based on this consideration alone.
I think two flavor adjoint QCD with like n, I don't know, 3 or 4 would work, because in that theory you have a Z-n center symmetry.
Right.
But also there should be a Goldstone boson, assuming that it has the expected pattern of spontaneous symmetry breaking. And I would guess that the center symmetry should not be spontaneously broken.
Yeah, I think I agree.
But does it become some decoupled sector, or?
No, I think it just expected to confine and be gapless. There's some zero form symmetry breaking.
Yeah, exactly. Some continuous zero form symmetry breaking.
But I mean, that's the situation in like massless QCD also, right? Like it's confined.
Yeah, exactly. Exactly. It's just a massless QCD doesn't have a one form symmetry.
Doesn't have a one form. No, I understand, but I didn't mean that directed at you, Alexia. I meant it directed at Ifan.
No, but what I meant just that I understand that in confinement, of course, the one form symmetry is preserved. But I'm saying that here, are you assuming that this one form symmetry will also act non-trivially on the gapless sector, rather than just?
No, it could act trivially on the gapless sector. I don't know. I'm making I don't know. This argument, in my opinion, is too stupid to tell the difference. Maybe more sophisticated arguments can, but this was made some very brutal assumptions.
But would you say that in the end, it's the one form symmetry just always spontaneously broken in this case?
No, I don't. I don't see why I would say that.
But if the theory is gapless, then
if the theory is gapless, the argument doesn't really apply, because I sort of, to evaluate the partition function, I assumed that it was gapped. So I always had that as an out, because it was one of just.
I see. You say just okay. I see. Okay, that's fine. Yeah, I think I was assuming something stronger when you say it's enforced to be gapless. Right. But that's fine. Yeah.
I have a possibly very silly question related to this. In the arguments where you had to assume the theory is gapped, were you also working on a compact manifold or not?
Here, well, what I meant is that it's what I meant is that here is that there's a finite number of states really on every spatial slice. So it's I mean, I was using gapped in the sense that I meant that the infrared is a TQFT.
I see. Thank you. Mm-hmm.
That's why the partition function calculation becomes so simple. It's just that matrix element times some finite degeneracy.
I see. I see.
Can you generalize this story to 3D?
Well, in fact, let me refer you to the very nice paper by Omori, Katie, and Zhang, who in fact did come up with some nice 3D examples. It's their work, but so you should read their paper. But the main point is that if you go back up here, where was it? Here, I said that if you get, I had this constraint that that if you gauge, say, a Z and Q form symmetry, you can only go back to yourself if Q is 0 and D is 2, Q is 1, D is 4, Q is 2, D is 6, etc. But that that is just an artifact, really, of the simplifying assumption that G was this simple group. You could say maybe G is like a 1 form symmetry times a 0 form symmetry. Then in 3 dimensions, you could be invariant under gauging the product.
I see.
And that is indeed the nature of the examples that they constructed.
Mm-hmm. Also, if I make G not finite, but say U1, in 3D, if I just study the 3D Wilson feature, O2 Wilson feature, and gauge the U1 symmetry, I get back to the same theory. Is it possible to define some kind of such duality defect in that context?
Yes, it's probably possible. You'll encounter some additional subtleties, which is that that I'm not sure exactly how to deal with. For instance, the gauge field is not flat in general. So I'm unsure about the topological nature of that defect. And also RG doesn't really commute with the dynamics. So the nature of all these kind of arguments that I had about constraining the long distance behavior given some self-duality will be more subtle. On the other hand, the duality that you mentioned is really an infrared duality anyway. So maybe I'm not sure. I'm just not sure. But it sounds interesting to think about.
Thanks.
Any more questions? I think in any case, we should thank Clay for the wonderful seminar. Thank you very much. Thank you, Clay.